So in order to think about how the trans effect actually works, we need to think about the mechanism of substitution in square planar complexes. So here we're going to walk through it step by step. So we have our metal, and it's square planar, and we're going to draw it sort of on its side like this in order to help us visualize what's going on. So the L ligands are just spectator ligands, they're just hanging out. The T ligand is the transdirector ligand, and X is the leaving group. Okay, so on this complex, on the metal, there is a p orbital that is just waiting for, so an empty p orbital on the metal that's just waiting for a Lewis base, a new ligand, to come in and make a bond with it. So that's the first thing that happens, is that we can imagine that the new ligand associates. So we're going to call that the incoming Y ligand on the square planar face of the complex. So first thing that happens, new ligands associates. This is an associative mechanism. Then this sort of intermediate transition state, the line here is really fuzzy, rearranges a little bit. So the first geometry is square pyramidal. But we know that these ligands can get a little more space from each other if we make a trigonal bipyramidal geometry. So this rearranges a little bit so that we have trigonal bipyramidal. And we're going to show that basically the X ligand, what's going to be our leaving group, swings around to get further away from Y. Then what happens, so in order for the reaction to keep going, we need to start making something that looks like the product. So we can imagine that these ligands are still moving around a little bit, but now we're going to move around so that the incoming ligand is trans. So we have a square pyramid, but now the incoming ligand is trans to the transdirecting ligand. That basically, you can see that we have something that starts to look like the product if we just break that metal leaving group bond. And so that's what happens next. We imagine that the X ligand leaves, and now we have Y in place of where X was, trans to the strong transdirecting ligand. Okay, so these are the steps that we imagine happening as our square planar complex is substituted. And so then we see that our trans effect is going to be based on two different possibilities. One of them, we're going to call the trans influence, is related to weakening the metal X bond. The other one is in producing, how we produce this 5-coordinate intermediate transition state. And so the potential energy diagrams that we are representing here are showing that effect. So if we imagine that like normal substitution happens in two steps, an associative step and then a dissociative step, we can think about the activation energy of that first step as being rate determining. So if we're able to weaken the metal leaving group bond, then basically what we're doing is we're raising the energy of that starting material. So let's imagine that we raise the energy of the starting material, but we're keeping the energy of the transition state about the same. So in that way, we can decrease energy of activation if we can make the reactant sort of more reactive. So this is the sort of first effect, and we're going to call this the trans influence. And this, because we're changing the energy of the reactants, is a thermodynamic effect. The other way that the trans effect works is what we call sort of the real trans effect. In this case, we're lowering the activation energy of a particular transition state. So we're going to keep the starting energy the same, but we're going to lower the energy of the transition state. So in the same way, we're going to make energy of activation smaller, So we see that our activation energy is smaller than it was in the other one. So basically we have many possible transition states, but we're going to favor one particular one that results in substitution trans to the strong trans-directing ligand. So this is going to be what we call the trans effect. And this is a kinetic effect. And so the next couple of slides are going to be about how that effect works.